This is lecture number 6. I promised the last lecture in which I will torture you with matroids, but I promise also that this is going to be beautiful mathematics. The lecture is about the matroid intersection problem, in which we try to find maximal sets which are independent in two different matroids simultaneously, defined on the same ground set, obviously. And this increases the modeling power because we can look at problems which can be modeled by the intersection of two matroids and not just one single matroid. And the main part of the lecture is about an algorithm to find such maximal independent sets in two matroids simultaneously, which is due to Jack-Edmonds. In order to get there, we need a little bit more insights and basic definitions on regular matroids. Then I will define the matroid intersection problem more formally. We will be working with a so-called augmentation digraph, in which we again try to find so-called augmenting paths. And finally, I explain matroid intersection algorithm itself, which, with all the work that we have done before, is then quite simple. So let us first recall the definition of a regular matroid due to Whitney in 1935. So we have a universe of elements, a ground set E, that's a finite set, and this curly I is a collection of subsets of this set E. And this is called a matroid if, first of all, it contains the empty set. Then it is downward closed, which simply means that if I have an independent set J, then any subset of J is also independent. And the most important property that actually defines a matroid is the augmentation property, which says that if I have two independent sets I and J, one smaller than the other, so the cardinality of I is smaller than the cardinality of J, then we can find an element E which is contained in J and not yet in I, such that we can augment the smaller set I by this additional element. And I guess everybody must have noticed a little typo here. This E and S refers to the same element. And as you can see, magically, now the typo has been fixed. The collection of subsets of this ground set E is called an independent system if it only fulfills these two first properties, so downward closeness, and this property M3 actually makes this independent system a matroid. Now we had another characterization, an equivalent characterization of matroids in terms of basis, and let me also recall that one. So a basis is just defined as a maximal independent set. So that would be a basis of the matroid. That's just an inclusion maximal independent set that cannot be augmented by any element without becoming dependent. And we can also define basis of subsets Q. So you pick a subset, a fixed subset Q of the elements, and you can also look at maximal independent subsets of Q. And that would be called a basis of Q, you know that. And by this, we also already know that the maximal independent subsets of a given subset Q, they all have the same size. And therefore, we can define the rank of a subset Q as the size of the corresponding basis of that subset Q. And that is well defined because if we talk about a matroid, which fulfills this property M3, this is equivalent with fulfilling this property M4, which just says that all the bases of every subset Q of the universe of elements E, any two bases of that subset Q have the same size. So that makes this rank well defined. And so is the rank of the matroid, which is the size of the maximal independent sets of the whole matroid. Thinking about the matroid defined by forests in an undirected graph, that would be all the spanning trees, that would be the maximum independent sets of the whole matroid, and they all have the same size, namely number of vertices minus 1. Now, as I said, we need a few more definitions about matroids. And the first definition that we need, or the most important one for this lecture, is that of a circuit. So a circuit is just an inclusion minimal dependent set, not independent. So think of the previous example of forests in a graph, also known as the graphical matroid. Okay, so we are given an undirected graph G. First of all, what would be the independent sets of this graphical matroid? We know that that's the set of all subsets of edges which do not contain a cycle. And now what is the inclusion minimal sets which are not independent? Well, that would be the cycles itself. So for example, this little example graph here has a whole bunch of circuits. I didn't write them down all. So that would be all these cycles here of length 3, for instance, but also longer cycles of length 4. Also, this one is a cycle. So all of them have the property that whenever I take out a single edge, then I obtain an independent set. Okay, so the definition of a circuit is an inclusion minimal subset which is dependent. So therefore, that must be a cycle in the graph. And also notice that the size of these inclusion minimal sets, so the size of these circuits, is not necessarily the same. We have circuits of size 3 here, but also longer circuits. So once again, a circuit is defined as an inclusion minimal dependent set. So whenever I take out an arbitrary element from this circuit, I obtain an independent set. So like on the previous example, the cycles of the graph. Now, having defined circuits, we come to our first little lemma, and that is the following. If you give me two different circuits of the graph, C1 and C2, and assume they have a common element, E, which is contained in both C1 and C2, then this little lemma says there exists a circuit C as a subset of C1 and C2, not containing this joint element of the two. And I think this is best seen again in the graphical matroid example. So if you take this graph G here, okay, and let's look at two circuits for this graph. So there is the red one here, C1, and the blue one here, C2. And as you can see, they share a common edge, namely the edge in the center here. And what does the lemma say? Well, there exists a circuit C, which consists only of the blue and red edges, but which does not contain this middle edge. And that is this green circuit C here on the right of the figure, right? So let us look at the proof of this little lemma. So once again, the claim, I have two different circuits, C1 and C2 of an arbitrary matroid. I have a common element E contained in both C1 and C2. So then the claim is there exists another circuit C only consisting of the elements of C1 and C2, not containing the shared element E. So what we're going to show is that the union of these two circuits, C1 and C2, without this element E, is itself a dependent set. Okay, and if this is a dependent set, it must contain some circuit. Okay, so let's assume for contradiction that this is not the case. So our assumption for contradiction is that the union of these circuits without element E is itself an independent set. Now let's see. So first of all, we know that C1 and C2 are different. So therefore, I can always pick an element F contained in the first circuit C1, but not in the circuit C2. And since C1 is a circuit, when I take out an arbitrary element, so C1 without F, that is an independent set. So this independent set here, I can extend it to a basis. So I extend C1 without F to a basis of what? To a basis of the union of these two circuits. Okay. Let us call that Z. So once again, what is Z? Z is the basis of C1 and C2, maximal independent set, and it contains the circuit 1 and does not contain element F. Now, is that really true? Yes, it is. So first little observation, whoops. Then F is not contained in this basis Z, because otherwise the whole circuit C1 would be a subset of Z, but Z is an independent set and C1 is a circuit, right? So that cannot be true. Also, it is clear that C2 cannot be completely contained in Z because of the same reason. Z is an independent set, it's a basis, C2 is a circuit, it's dependent. So since C2 is not contained in Z, it must contain some other element, so there exists an element F prime which is contained in C2 but not in Z, and this element F prime is not the same as element F. Why is that? Well, that is simply true because F was chosen to be in circuit number 1 but not in circuit number 2. So therefore the element F prime, which is member of C2, cannot be F itself, which is not contained in circuit 2. So now I know that this basis Z, which was chosen to be a basis of C1 union C2, it is not containing element F, and it's also not containing element F prime. Okay, but now let's look at the size of this basis Z. Okay, so what can I say about the size of this basis Z? Well, it's certainly not larger than the size of this subset. Okay, so this is smaller or equal than the cardinality of C1 union C2 without these two elements F and F prime and F, which again is certainly strictly smaller than the union of C1 and C2 when I just take out a single element, E. Notice that I have this strict inequality here, because here I'm taking out two different elements, F prime and F, and here I'm taking out a singleton element from this union of C1 and C2. All right, now we have to remember what the assumption in this proof was. Our assumption was that the union of these two circuits without element E is an independent set. Okay, so let me copy that here. So this is an independent set. Okay. What again was this set Z here that was supposed to be, or by definition, a basis of the union of these two circuits, C1 and C2? And I claim that I now have a contradiction. Why is that? Well, I have an independent set here that is C1 union C2 without element E, and this independent set could be further extended to a basis of C1 and C2, okay? Or it's actually, it is the basis itself. And this has strictly larger cardinality than this set Z, which was also a basis of C1 and C2, okay? So we have two bases. One is Z here, with strictly smaller cardinality than this subset, which can still be extended to a basis. So we obtain two different bases of C1 and C2 of different sizes. And that is actually a contradiction to the fact that we have a matroid here, because in a matroid, all the bases of subset C1 and C2 must have the same size. And that's the end of the proof of our first little lemma on matroids and circuits. Okay, so whenever I have two different circuits, C1 and C2, which share a common element E, I can find a larger circle C consisting of the elements of C1 and C2 not containing this joint element E. So this per se is not extremely interesting, but it has a very important consequence, which is this so-called uniqueness lemma. Okay, so if you give me a matroid, an arbitrary matroid, and an arbitrary independent set X, okay, and an arbitrary element from the ground set, then two things can happen. When I add this element F to the independent set X, it could still remain independent. For example, F could already be contained in X, or it's simply feasible to extend independent set X by this element F. Or, I mean, if it's either it's independent or it will be a dependent set, that's the other case. And because I just added a singleton element and X was independent before, the important consequence now is that this dependent set, it will contain a circuit, but actually not just some circuit, it will be a unique circuit. So there is a unique circuit contained in this dependent set X union F, and therefore later on we can give it a name that is the circuit induced by independent set X, an additional element F. So let us quickly see how I can get this uniqueness lemma. So here is again the repetition of the claim. I take an independent set X, I take an element from the ground set. Either if I add this element to set X, it still remains independent, or it will be a dependent set, and then it certainly contains a circuit, but the claim here is this circuit is going to be unique, and I give it this particular name here. So for the sake of contradiction, let's assume we have two different circuits, C1 and C2, contained in X, including this new element F. Now, because X was actually an independent set, it cannot be the case that, that C1 is contained in X, and it can also not be the case that C2 is contained in X, because X is an independent set, whereas C1 and C2 are circuits. So they are not contained in X, and therefore the only possibility is that these circuits must contain this new element F. Okay, so F is contained in C1 and in C2. But now we remember our previous lemma, right? Because we now have the situation that these two circuits, C1 and C2, they have a common element F. And by applying the previous lemma, we know that there exists a circuit, let's call it C, which is made of the elements of C1 and C2, but does not contain the shared element F. But now C1 and C2 are subsets of this set X and could potentially also contain element F. So when I take out this element F, then this whole thing here must be a subset of X. Okay, let me write that down. So this is a subset of the set X that we started with, but X was actually assumed to be an independent set. And now again, I obtain a contradiction. Why? Because I have a circuit C, okay? It's a circuit in the matroid, and it's a subset of an independent set. That is impossible. And I should write that this is a subset of X. Sorry for that. But in any case, we have a contradiction, and that is already the proof of this uniqueness lemma. So this is what we have proved, this so-called uniqueness lemma, which says that when I have an independent set X, and I try to augment it with an arbitrary element E, then either this still remains independent, I'm fine, but if it becomes a dependent set, then it contains a unique circuit, okay? This is essentially intuitively because I started out with an independent set and I augmented it with a with a single element only. So this results in a unique circuit, and it will be denoted, or it will be given a name later on. So this was a little bit preparation for a lemma, and a so-called exchange lemma that I'm going to prove next. But before I do that, let me give you a kind of idea what the goal is that we want to achieve. So at the moment, I'm still talking about a single matroid, but in a minute we will have the situation that we have a set X, which is independent in two matroids actually, and we would like to augment it. We would like to add new elements to X one by one, but we could be hindered by adding new elements due to the fact that whichever element I would like to add to X, it either becomes a dependent set with respect to one or the other matroid, or maybe both. Okay. So in order to proceed later on in the algorithm, we might have to exchange some elements from X. So elements which are already sitting in X by other elements which are not yet sitting in X, without changing the cardinality of X actually. And but once I have done such an exchange, maybe it's then possible to augment without violating any of the two matroid constraints. So essentially what I'm heading at is an exchange lemma that tells me why or how I can do such exchanges. So let me formulate this exchange lemma. And as announced, I will be denoting by Cx, F the unique circuit contained in the set X union F. Okay, so I start with an independent set X. I take an arbitrary element out of the ground set. And if adding element F results in a dependent set, no longer independent, then this Cx, F denotes the corresponding unique circuit, which one could say is generated by an independent set X and an additional element F. And if, on the other hand, adding element F to set X still results in an independent set, this unique circuit is just defined as the empty set. Okay, so this is how the exchange lemma looks like. It's quite a mouthful, but it's not really that complicated. So what I do is I'm currently sitting with an independent set X, and essentially I want to exchange a couple of elements, E1 up to ES, which are currently sitting in X, by other elements F1 up to Fs, so the same number of elements which are not yet sitting in X, in such a way that the result is still an independent set. Okay, so I started out with an independent set. At the end, I will again have an independent set, and I will have exchanged all the elements E by all the elements F. And I just do that, or you should think of doing that one by one. So I'm exchanging E1 by F1, E2 by F2, and so on. And in order to understand these two conditions, which have to hold for the final conclusion to be true, look at the first element, say. Okay, so when I add the first element F1, or on a later iteration, an element Fk to the set X, I could generate a circuit, right? So I could get a dependent set. At the end, I want to be independent again. So I have to kick out an element, and that is an element Ek, which actually can be thought of as destroying the corresponding circuit that I got by adding element Fk. Okay, so Ek will destroy the corresponding circuit so that after I have exchanged Ek with Fk, I'm still independent. Now that's the first condition, which is kind of intuitive. The second condition here is maybe a little bit less intuitive. It can be thought of as a condition that makes sure that the circuits that I create and destroy one after the other are disentangled enough. And technically what it says is that all the elements Ej that I already had kicked out earlier, these should not be part of the circuits generated by adding later elements. So whenever I add a later element Fk to X, then this second condition makes sure that the circuit that this element fk generates when it is added to X, it's still the same circuit even if I earlier kicked out a couple of the other E's. Okay, so that is these other elements E with a smaller index. So that's the elements that have been kicked out from X earlier. And these elements should not be sitting in the circuit number K. So it will become clearer when we look into the proof. But before doing the proof, I would like to look at one or two small examples, what this exchange lemma actually does. So let us do that. So you see here a graph on 5 vertices. We have an independent set X. So this is an example from the graphical matroid again, which is nicest to visualize. So we have an independent set X, which is these 4 edges here. And we have edges which are not in the current set X, which is this edge F1 here, which closes this red cycle, this unique red cycle. We have this edge F2 here, which closes this blue cycle, and F3 here, closing this green cycle. Okay. Now, the conditions of the lemma say, okay, so if I want to add an edge F1, I have to destroy the corresponding cycle that I generate, and I do that choosing or eliminating edge E1 from X. Same for this one. So when I add F2, then I create this blue cycle here. So cycles are now circuits. And in order to destroy this cycle, I eliminate edge E2, and the same here for the third cycle, right? So E1 is an edge that sits in the first cycle that I would generate. E2 is an edge that sits in the blue cycle, and E3 is an edge that sits in the green cycle. And when I look at condition number 2, this condition says that the first edge here should not be part of the circuit generated by later elements, so by the circuit generated by element F2, and also not in the circuit generated by element F3. And this is actually true, because this is the edge E1, and it's obviously not part of the blue circuit down here, and also not part of the green circuit down here. And also edge number 2, which is this edge here, should not be sitting in the green circuit, and also that is fulfilled. And now the lemma says, okay, all the conditions are fulfilled. I can exchange all the edges E1, E2, E3 by F1, F2, F3 and still obtain an independent set. And indeed, this is the case. So if you look in the upper picture, I'm kicking out E1, E2, and E3, and I'm adding F1, F2, and F3. And by doing that, indeed, I still get an independent set, so it's still cycle 3. So this was just a verification of all the conditions of the lemma and that they are fulfilled, and then that indeed the lemma says the right thing, namely that what I get by the exchange is still an independent set. But to understand what's going on, it's even more instructive if we look at the situation step by step. So if we do the exchanges one by one, and to that end, look at this picture. So same example. So let us first look at the upper example again. That's the same as before. F1 is closing this cycle, F2 is closing that cycle, F3 is closing this green cycle here. And then the first step of the exchanges would be exchanging E1 by F1, and then we would obtain the corresponding spanning tree in thick black here. And the important thing to realize is now that if I after that do the exchange F2 against E2, it's still the same cycle. It's still the same cycle that we had here in the beginning. And also in the last step, when I do the exchange E3 against F3, I'm still talking about exactly the same cycle as I had before, right? So that is what the condition number 2 actually guarantees, that at the moment that I look at the exchange of E3 against F3, that this is just exactly the same cycle as the one that we had in the beginning when we were setting up the conditions. Okay, and well, we already figured out that for this example, the lemma works. And the bottom example down here shows how this could go wrong. So essentially, this looks like the exact same situation as before. We have these three triangle cycles here in red and in blue and in green. And there is only one condition that we are failing, namely the situation here is that this edge E1, which is the edge that we exchange against F1, so that is destroying, after all, this red cycle here. It's also an edge that appears in a cycle induced by F3. Okay, so this edge, so the condition that is violated is this one, namely that edge E1 should not be in the circuits induced by adding later elements with a larger index. Okay, so there is a violation of the conditions, and let's see what that induces and what goes wrong. So after the first exchange of E1 against F1, we obtain this spanning tree here. After the second exchange E2 against F2, that is still okay. We get this spanning tree here. So at the moment, everything looks nice. But now we have the situation that we, when we look at adding edge F3, this would close another cycle, namely this large triangle here. So this edge F3, because we have already eliminated edge E1 here, is closing a different cycle than the one we identified earlier. And this is exactly where it goes wrong. Namely, if I now do the exchange F3 against E3, that is not even, so this edge E3 is not even part of this cycle, and therefore this exchange actually won't work. And indeed, if I do the exchange, the result will be a dependent set, namely this large cycle of length 3. So the lemma fails on this example, well, of course, because it's violating one of the conditions, but more intuitively, because there is an entanglement of these two cycles, the red one induced here on the right-hand side and the green one on the left-hand side via this edge E1. And the removal of this edge E1 has as effect that F3, when adding F3, we are again generating a circuit, a cycle in this case, but not the one that we had before. So in order to eliminate this cycle at the end, we would have to remove another edge. So having seen this intuition on the graphical matroid, I think we are set up to look into the formal proof of this exchange lemma, and this is what I do next. So one final time, what is the lemma? We have these elements E1 up to ES. We have in X, we have S1 up to Fs, not in X, fulfilling our two conditions, number 1 and number 2. And the claim is that removal of all the E's and addition of all the F's creates an independent set again. Now I make one definition for each index R between 0 and S. I define the set XR, which is, you could see that as the rth step in the iterative procedure, where I first exchange E1 by F1, that gives me X1. Then, having done that, I exchange E2 by F2, that gives me set X2, and so on. So at the end, we will have exchanged all the elements, and XS is actually the set that we want to be independent. And we show even more. We show that when I do that in this iterative fashion, that all these sets XR are actually independent. So in particular, then also at the end. Now, as an inductive, it's an inductive proof, induction on this index R. So on these sets XR. And inductive start would be, well, what is the first set? So x0 is just x itself that was independent by assumption, so that's fine. And as hypothesis for the inductive step, I assume that set xr minus 1, with index r minus 1, is an independent set. And I would like to show that set xr will then also be an independent set. What is xr? Well, I take xr minus 1, I add element fr, and I remove element er. So we have to show that this set xr, this set xr is an independent set. Well, the trivial case is if the addition of the new element fr still leaves an independent set. So if xr minus 1 together with the element fr is still independent, well, then we are done. We don't even have to remove element er. So that is fine. And otherwise, this will create a dependent set, and then we have to show something. So if this creates a dependent set, it will contain, because by assumption xr minus 1 was an independent set, it will contain a unique circuit, so which we have denoted as the circuit induced by set xr minus 1 and the element fr. Now we know that by condition number 2, that all these elements with index smaller than r, so that is the elements e1 up to er minus 1, they are not contained in the corresponding circuit induced by x and element fr, which means this is a subset of x without all these elements, e1 up to er minus 1, together with fr, which again by definition is a subset of x r minus 1 together with fr, because the latter one, so this one may only contain even more elements, so f1 up to fr minus 1. And now observe one thing. We have a circuit, so this is a unique circuit induced by set xr minus 1 and by adding element fr to it. And we have here another circuit, which is also a subset of xr minus 1 together with the rth element fr. But by the uniqueness lemma, we know that this dependent set contains a unique circuit. So therefore, this circuit and this circuit must be the same. So let me write that down. So the uniqueness lemma gives me that the circuit xfr is just the same as the circuit xr minus 1 fr. And remember, that was the same situation like in the previous examples. So when I reach this iteration number r minus 1 here, we are still talking about the same circuit. Okay, so now we look at condition number 1, which says that element ER, that's actually an element that is in the circuit induced by adding element FR to X. Okay, so I just write that down. So ER sits in the circuit induced by X and by adding FR. And as we just said, this is the same as the circuit XR minus 1, adding element FR. And now remember what the definition of a circuit is. So now I have an element ER, which is in this circuit here. A circuit is an inclusion minimal dependent set. So I have an element from that inclusion minimal dependent set here. So when I remove this element, I get an independent set. And that actually implies the following, namely that if I look at the set xr minus 1 together with element fr and without element er, this must be an independent set. Why is that? Well, this set This set here contains a unique circuit, which again contains element ER. That is what we just figured out. So this set contains the unique circuit in this set contains element ER, and when I remove element ER, I must get an independent set. But now we are done because this is exactly set XR. And that is what we had to show, namely that set XR by induction on R is an independent set. Well, that finishes the proof of this exchange lemma. And as you have seen, we actually needed both conditions, right? We needed a condition number 2 in order to figure out that, well, in some sense, the circuits remain the same in the course of the proof or in the course of the algorithm. And we needed condition number 1 in order to get that this element number R is actually contained in the corresponding circuit, which is the same circuit after we have removed a couple of elements already. All right, so this finishes the proof of the exchange lemma. I'm not going to repeat it again. And now we have all the technical equipment ready in order to move towards matroid intersection and an algorithm to solve the matroid intersection problem. So next I'm going to define the matroid intersection problem formally. So let me define the matroid intersection problem, or first the intersection of two matroids. So we start with two matroids M1 and M2, and we are interested in subsets which are independent in both matroids. Okay, so that means we're interested in the structure M3, which for the moment we might call a matroid. And a set is independent in M3 if and only if it's independent in both matroids M1 and M2 here. Okay. Unfortunately, the name is not correct, so M3 is not. So this is a subset. This is a collection of subsets again. It will contain maximal independent sets and so on. But unfortunately, it's not a matroid. So matroids, if you wish, the combinatorial structure matroid is not closed with respect to intersection, because the intersection of two matroids is in general not a matroid. And we have seen examples of that already. So let me remember you. The simple example for graphical matroids is if we consider bipartite graphs, okay, then we know that we can express matchings in bipartite graphs as the intersection of two matroids. And if you forgot how that works, I will explain it on the next slide with a little example. But we know that matchings in graphs and also in bipartite graphs are generally no matroid structures. Okay, so I think it helps to look at the example here. So we start out with a bipartite graph. On the right-hand side, you see the graph. And we say, we define an independent system I1 by saying that a subset of the edges such that the degree of a vertex in F is at most 1 for all the vertices in A. So that means the degree of all the vertices here on the left-hand side is at most 1. And the blue subset of edges, that is actually an independent set with respect to this independent system. Okay, so the degree constraint is maximally 1 for the A vertices, and symmetrically we define the other matroid in the same way, requiring that the degrees are at most 1 for the B vertices here. We had an exercise showing that is A-sided and B-sided matchings, and we had an exercise on the first set of exercises where you showed that A-sided matchings and by symmetry also B-sided matchings are actually matroids. Okay, so these subsets of edges define matroids. And now what is the intersection of these two matroids? Subset F of the edges would be called independent if it sits in both matroids, in both independent systems here. So that means the degree of the A vertices should be at most 1, and the degree of the B vertices should be at most 1. right? So the degree of all the vertices should be at most 1. So I'm looking for a subset of edges such that the degree of the vertices for this subset of edges is at most 1 for all of the vertices. And that's exactly the definition of a matching in the graph, right? So that's a subset of edges that do not meet each other, because as soon as they would meet each other, we would have a degree of 2. All right, so we have defined matchings in bipartite graphs as the intersection of two matroids, but matchings in bipartite graphs are not matroids themselves. Why is that? Here is a little example. Consider the dark green edges here. That's 2 edges in this bipartite graph. And the light green edges is 3 edges. Both are matchings in this bipartite graph. And if it was a matroid, we should be able to extend the smaller set, so the dark green edges, by selecting one of the light green edges, right? Because it has 1 element more. But this is not possible. So we cannot get a matching. So we are violating the augmentation property for matroids. And indeed, matchings and bipartite graphs are not matroids. But of course, that is not the end of the story, because we already know that we have efficient algorithms to compute matchings, not only in bipartite, but even in general graphs. Okay, so it's really not the case that the only combinatorial structure for which we have efficient algorithms would be matroids. But an interesting question would be if, well, the fact that we can efficiently find matchings in bipartite graphs, is that a coincidence, or is it maybe due to the fact, can it be attributed to the fact that matchings in bipartite graphs can be expressed as the intersection of two matroids? And that is the question. So can we find efficient algorithms for combinatorial structures, say maximal or minimal basis, for subset systems which are defined as the intersection of two matroids? Yes or no? And that is the matroid intersection problem. Given 2 matroids, we want to compute subsets, maximal size subsets, maximum cardinality subsets, which are independent for both matroids. In the more general version of the problem, we would even have weights on the elements, and we would like to, say, maximize the total value or total weight of the elements that we select. But here we only consider the special case where all these weights are equal to 1. So that would mean we are looking for cardinality maximal independent sets in 2 matroids simultaneously. And that's the definition of the matroid intersection problem. Now, how do we compute sets which are independent or maximally independent with respect to 2 different matroids? And the basic idea is just as with earlier problems, we start out, for example, with the empty set or some given set, which is independent with respect to these 2 matroids. And then we try to augment it. And we do these augmentation steps in a so-called augmentation digraph. So let me try to explain how this works. So we have some independent set in both independent systems, and we define Sx and Tx as subsets of the elements in the following way. So Sx would be the elements that I do not yet already have, which can be feasibly added with respect to the first matroid. And Tx would be the element that I don't have already, which could be feasibly added to with respect to the second matroid. Okay, so that's the 2 subsets which are interesting. So that's given the current X, those that can be feasibly added with respect to either one or the other matroid. Now, first of all, one question. What if one of these sets is actually empty? So if Sx or Tx is empty, well, that means that we have an inclusion-wise maximal set with respect to one of the 2 matroids. So let's assume for matroid number 1. Okay, so if Sx is empty, then we have an inclusion-wise maximal set, so no element can be added anymore to the set X that we currently have. So we have a basis in the first matroid, and that means that the cardinality of X is maximal for the first matroid, right? Remember, because this is a matroid, the size of all the bases are maximal. So this is a maximal set already for the first matroid, and hence we anyhow cannot augment it. So therefore it will also be maximal in the intersection of the two matroids. So that's kind of the simple case, and in that case we would already be done. Now, if on the other hand, and that is the second thing that could happen, if I find an element which is contained in both sets as X and Tx, that means I have found such an element F that can be feasibly added to X with respect to the first matroid and can be feasibly added to X with respect to the second matroid. Then I can just augment by this element and I'm still independent with respect to both matroids, and I'm also done. Okay, so the interesting case is the third case, namely when the intersection of these two sets as X and Tx is empty. Okay, so that means I cannot just simply add a single element because it would become infeasible with respect to either one of the two matroids, or maybe even with respect to both. And in that case, I might have to exchange some elements for other elements in order to get a situation where I possibly could add a next element. Remember, we want to augment X by one additional element. And in order to get that done, I can construct this digraph dx in the following way. Well, first of all, the vertices of this digraph is going to be all the elements, and I split them up into the elements that I've already chosen, X in pink on the left-hand side, and the elements that are not yet contained in X in blue on the right-hand side. Okay, I also will depict these two sets Sx and Tx into this bipartite graph. So that would be these dark blue subsets of elements. So remember Sx, that would be elements that I can feasibly add with respect to the first matroid. So feasibly add to the set X with respect to the first matroid, and Tx were those that I can feasibly add with respect to the second matroid. And the whole picture makes sense. Since these two sets are disjoint, that was our assumption, these are actually not overlapping. So the picture is correct as it is. So that's the vertices of this directed bipartite graph. And now in order to, I'm going to introduce edges, but let me first try to explain the basic idea. So consider such an element in Tx down here. It could be feasibly added with respect to the second, but not with respect to the first matroid. Okay, so if I add such an element, I will create a dependent set with respect to the first matroid, and that is, it's going to induce a circuit, right? Now I can wonder, okay, if I would like to include such an element here, then I probably have to kick out one element from the left-hand side, from the set X that I already have. And okay, if I want to include this one, I might have to kick out that one, and then I just introduce a directed edge from left to right. Okay, so that's the idea. And I do that for all the vertices on the right-hand side with respect to the first matroid, first of all. So I'm introducing all these directed edges from left to right. Okay, so from E to F. So that's edges directed from left to right, where F is an element that I might want to add, and E is the corresponding element that I would have to kick out, or that I can kick out in order to destroy the corresponding circuit that I would get. Okay, so that would be feasible exchanges of elements E for F with respect to the first matroid, and as I said, all directed from left to right. So that's one set of arcs or edges, directed edges in this digraph. And now I just do exactly the same thing with respect to the second matroid. Okay, only difference is going to be that I now direct all these edges from right to left. Okay, so I have, first of all, I explained these directed edges A1x from left to right, and now I introduce the same sort of edges, only all directed in the other direction with respect to the second matroid. Otherwise, the idea is exactly the same. That is going to be feasible exchanges of elements for each other. So F is always the element that I could or would like to add, and E is an element that I can use in order to destroy the corresponding circuit that I will get. And that already finishes the construction of the whole digraph. So dx denotes the digraph, directed bipartite graph actually, with as E all the elements in this way, and these two sets of directed edges. Now, how does this help? Well, let's look at a small example. That would be this one here. And let's consider the situation that we find or have a directed path that leads us from Sx to Tx, and the shortest possible or the simplest possible way to get that is via two directed arcs, right? Then what is the significance or what is the meaning of such a path? Well, first of all, we know that we can add this element F0 with respect to the first matroid, okay, but not with respect to the second one. And likewise, this one could be added with respect to the second matroid, but not with respect to the first one. Now, what does this edge mean, or this directed edge mean? Well, that means if I add this element, then with respect to the second matroid, I'm getting infeasible, but this infeasibility can be get rid of. I can destroy the corresponding circuit by removing this element E1 here. That's the significance of this arc. Likewise, when I add element F1, I get something that is infeasible or dependent with respect to the first matroid. And how can I get rid of this dependence or infeasibility? Well, the significance of this arc tells me that I can kick out this element. And that means that I have one and the same element that I can kick out, which destroys both infeasibilities with respect to these two different circuits, right? So once again, adding element F0 to the matroid, we would get a circuit with respect to the second matroid, and adding element F1, we would get a circuit with respect to the first matroid. And the removal of this one singleton element from X, here on the left-hand side, that actually allows me to kill both circuits. So that means after I have removed this element E1, and after I have added these two elements here, I'm again independent, okay? And so you see that this path, this directed path of length 2, is an augmenting path for the intersection of these two matroids, because I can add two elements while removing only one. So that is something nice. So this allows us to augment the size of the current set X by 1. Now this was one simple example. More generally, I can say, okay, so this should work also if I have paths longer than of length 2. And that is actually almost true. So let us just consider a path that leads us from the set, from the set Sx, from some element in Sx via some other vertices and edges to some element in Tx, okay? So I could do, or the idea is that I can still do the same. I'm exchanging these 4 elements here on the right-hand side by these 3 elements on the left-hand side, with the idea that, well, first of all, I'm adding one more element, so I'm increasing the size of the set X. But second of all, because this is a path, a directed path, it means that the corresponding circuits that I generate when I add these 4 elements will be destroyed by removing these three elements here, right? And it's going to be, in general, a path of even length from the set Sx to the set Tx. So that corresponds to a sequence of exchanges for the set X, right? So in some sense, you could see it in the following way. I exchange, once again, sorry. I exchange this element for this one, this for this one, this for this one. And now I can add this one for free. So that's basically the idea. And indeed, after I have done that, I have changed the set X to a set X prime, which now includes all these F elements on the right-hand side, and all the E elements on the left-hand side are removed, which is one less. So I have indeed increased my set by exactly one element. And that's the goal. So that means in order to augment the size of the set X by one element, I will have to find paths from Sx to Tx, and that's it. And that is exactly the key to Edmond's algorithm for matroid intersection. So we summarize all that in the so-called augmentation lemma. Okay, so let me just recollect what we said. We start out with an independent set, independent with respect to both matroids. We find a path which starts at a node F0 and ends at a node Fs, such that F0 was contained in the set Sx and Fs was contained in the set Tx. So that was this zigzag path of even length that I had on the earlier example. And actually now there is one small twist here. I will come to that in a second. This is actually a path from F0 to Fs, but it's going to be a shortest path. And here shortest means with respect to the number of edges again, okay? So if I do that, then the lemma says the following. Okay, if I have that, and if this is indeed the shortest path from the set Sx to the set Tx, then I can do the exchange. I can kick out the elements E1 up to Es, and I can therefore include the new elements F1 up to Fs and also the starting element F0. And this is exactly one more. And the whole result, so the set X prime, is still going to be independent with respect to both matroids, one might say by construction. And as by definition, this is going to be an independent set of size one more. But now, why did I say that I pick a shortest path from this node F0 to the node Fs? Okay, I didn't say anything about shortest paths before. So that's the question. Why do I pick a shortest path from the set Sx to Tx? And the reason is to fulfill the conditions of the earlier exchange lemma that we had in the beginning of the lecture. Okay, so whenever I pick a shortest path, indeed, this will guarantee me that this conclusion is actually true, namely that this is going to be independent with respect to both matroids. So really, it's essential for the proof to work to pick a shortest path. Okay. Now, of course, now you can guess that the proof of this augmentation lemma is going to make use of this earlier exchange lemma, and that is exactly the reason why we had the exchange lemma in the first place. So let us look at the proof, and let me just recollect once again what we want to prove. We have a shortest path, okay, that leads us from this set Sx to Tx, and then the claim is that the newly defined subset X prime, which contains all the Fs and which does not contain all the Es, that's again going to be an independent set, and that with respect to both matroids. So what do we show? Well, we make use of this exchange lemma, and actually we make use of it twice because we're actually having two matroids for which we have to prove the claim, right? And the trick is the following. So we first of all show that I can use, or I can apply this exchange lemma with respect to this independent set here. So that is the set X that I started with, and the first element F0. Remember that this is an independent set, because F0 was chosen to be an element of the set Sx, and that were the elements that could be feasibly added with respect to the first matroid. Okay, so this is still an independent set. And then the exchange lemma said something about possible exchanges of the same number of elements E by another set of elements F. Okay, so I show that the choice of these elements and this set actually fulfill the conditions 1 and 2 of our earlier exchange lemma for the first matroid. And then I show the same thing for the second matroid, only using different elements. So for the second matroid, element Fs was 1 because Fs was chosen to be of the set Tx, which were the elements that could be feasibly added with respect to the second matroid. So this is an independent set in the second matroid. And once again, I can show that this independent set and these subsets of items fulfill the conditions 1 and 2 of the exchange lemma also for the second matroid. Now, for the sake of this lecture, I'm just giving you the proof of the first claim, and the lecture notes contain the same argument, which is essentially symmetric also for the second matroid. Now, and the only thing that we have to verify is that these two conditions are really fulfilled so that we can apply the exchange lemma, right? Because the conclusion of the exchange lemma will that this will be a feasible exchange, exchanging these E's by these F's, and the same here, these E's by these F's, and the result in both cases is exactly the same. Namely, the result is going to be that 1 gives me, by use of the exchange lemma, that the set X prime is actually independent with respect to the first matroid, and 2 will give me that the set X prime is independent with respect to the second matroid. So X prime, X prime is in the intersection of these two matroids. Okay, let's see. Well, the first thing that I already explained, the exchange lemma was working on independent sets. And indeed, by our assumption or by our choice of this element F0, which was an element that could be feasibly added with respect to the first matroid, this is indeed an independent set. Next condition, the first condition was that whenever I add this element Fk, that potentially creates a circuit, then I have this element Ek, which destroys this circuit. So Ek is an element that is part of the circuit generated by this element Fk. Is that actually true? Well, for that, I just remember the definition of these directed edges with respect to the first matroid. So what was that? Well, that was all the edges EF, where F is an element that I don't have already, and E were exactly all the elements that I do have already, which are sitting in the corresponding circuit with respect to matroid number 1. So in the circuit with respect to matroid 1 for set X and the element F, and of course this is not the element F itself. Now because EK, so E1, F1 is an edge on our path, and EKFK is also an edge on our path. So that means the edge EKFK exists on the path and hence also in the diagraph that we have defined. So EKFK is actually such an edge, which exactly means if I have element Fk here, then Ek is an element from the set X that destroys the corresponding circuit, and that's exactly what I need, okay? So the first condition is fulfilled. And the second condition that we have to verify for the exchange lemma was this disentanglement condition, which says that element number J does not appear in the circuits generated by the elements Fk with a larger index K larger than J, right? So, but now just let's assume this would be the case. So let's assume that element Ej would be part of such a circuit Fk when K is larger than J. Now let me just copy paste the path that we use. So that's the path F0, E1, F1, etc. up to EJ, Fj, etc. up to Ek, Fk, and remember here our assumption is that index J is smaller than index K, okay, up to Es, Fs. So that is the shortest path that we were choosing in our directed augmentation graph, okay? So this is the shortest path in this directed graph, but now assuming that Ej, element number J, would be in the circuit when I add element Fk, that would mean that I can destroy this circuit here by eliminating or by taking out element Ej. But that would mean in our graph we would have this edge here, right? And now you see why it was important to assume that we pick a shortest path, right? Because, well, this was the shortest path to get from F0 to Fs. And the existence of this edge, shortest, by the way, with respect to the number of edges, and the existence of this edge would mean that there is a shorter path. So that cannot be. That's a contradiction to the choice of this as a shortest path, right? So here you exactly see the choice of a shortest path from the set Sx to the set Tx makes sure that we can prove that the second disentanglement condition for the exchange lemma is really fulfilled. So we have proved condition number 1 is true, we have proved condition number 2 is fulfilled, and therefore we can apply the exchange lemma, and that exactly means that this new set after application of the exchange lemma will be independent with respect to the first matroid. And as I said, I skipped the proof to show the same thing for the second matroid. It is essentially symmetrically the same argument, okay? So that finishes the proof of this important augmentation lemma. Now we have something to really construct sets which are independent with respect to both matroids, right? We might start out with an empty set, which is certainly independent in both matroids, and using this augmentation lemma and this directed augmentation graph, we can augment the set by additional elements, each time computing or trying to find shortest paths in this bipartite directed graph. So this already gives me an algorithm, right? I can augment and augment using shortest augmenting paths in this graph. But does that really work? So this procedure would certainly end if I do not find an augmenting path anymore. And that is the big question. Are we really done if we do not have any path from the set Sx to the set Tx in this augmentation digraph? Okay, so we need a proof that this algorithm, when this algorithm doesn't find any augmenting path or any such path anymore, that then we have computed a maximum independent set in these two matroids. So we would need a theorem that says the following. We have a maximal independent set in both matroids if and only if this directed augmentation graph does not contain a path from Sx to Tx anymore. That's what we would need. And to get there, we have to take a little detour, and that is again going to be a very nice duality inside that is even interesting in its own right. Okay, so here's the proposition, and the proposition is, I call it weak duality here. If we have an independent set in both matroids, then for all subsets of the elements Q, okay, the size of this independent set X is upper bounded by the sum of two ranks, namely the rank of the subset Q with respect to the second matroid plus the rank with respect to of the subset E minus Q with respect to the first matroid. And notice that you could exchange the roles, the rank functions of the two matroids here, because this is going to hold for all subsets Q. So I can as well use the same claim for the subset E minus Q, and then I would get the roles of the two matroids exchanged. Now, why is this helpful at all? Well, notice that this holds for any set which is independent for the two matroids and any subset of the elements. Okay, so whenever I now can find an independent set X and a set Q, subset of the elements, such that I get equality here, then I must have found a maximal independent set, right? Because, well, this is an upper bound for all independent sets, and whenever I have equality, I must have computed a maximal independent set. Just like with the flow duality, whenever I have a flow which achieves the same value as that of a cut, the flow must have been a maximum flow. Now let's look at the proof of this little weak duality proposition, and that's quite simple actually. Okay, so here I repeat the statement. We have an independent set for both matroids. We have an arbitrary subset Q of the elements, and then the size of this independent set is at most the sum of these two ranks. Okay, ranks with respect to the two different matroids, and then the set Q here and the complement of the set Q on the other side. So once again, the consequence is, if I happen to find an independent set X for both matroids and a subset of the elements Q such that I achieve equality, then X must be a maximal independent set for both matroids, because this right-hand side is an upper bound on the size of any independent set for both matroids, and I have achieved equality, so it must have been a maximum independent set. Now for the proof, let us just pick an arbitrary set X, independent in the two matroids, and an arbitrary set Q, subset of the elements. What can I say about the size of the set X? Well, the elements of the set X, that's the elements that are contained in Q, plus the elements that are not contained in Q. And now, what can I say about this subset? Well, X was an independent set. So this is also an independent set because we are talking about a matroid. So therefore, the intersection of X and Q is independent with respect to the second matroid. And it's also a subset of Q. Okay. And therefore, I can conclude that the size of this independent subset of Q is at most the rank of that set Q, so R2 of Q. Once again, this holds because the intersection of X and Q is an independent subset of Q for the second matroid. And now likewise, if I look at the other set here, X without Q, X was an independent set with respect to the first matroid. So when I take out elements, this is still independent. So here I have an independent subset of the set E minus Q. And therefore, this is upper bounded by the rank of that set with respect to the first matroid, rank of E minus Q. So once again, why is this true? Because X without Q is an independent subset of E minus Q for the first matroid. And that's already the end of the proof of this weak duality proposition. Okay, so now with this weak duality proposition at hand, we can formulate the crucial lemma that we need for the correctness of our augmenting path algorithm. And that's this augmenting path characterization. So what I mean is a subset X, which is independent in the two matroids, has maximum cardinality if and only if there is no augmenting path anymore in our directed graph, where augmenting path means a path from the set Sx to the set Tx. So that's exactly what we needed. And how do we prove this lemma, or this characterization of optimum solutions? Well, we show that if there exists no such path, no such augmenting path anymore, then we achieve equality in this weak duality inequality here, and therefore, by this weak duality proposition, we have achieved optimality with respect to the size of X. More precisely, we are going to show that if there is no augmenting path in this directed graph anymore, for a given set X, we can actually construct a subset Q of the elements achieving equality here. And this is exactly what I'm going to do next. So X is an independent set in both matroids so that no Sx Tx path exists anymore in this augmentation digraph. And now we're going to construct a subset Q of the elements achieving equality in this weak duality inequality, right? So achieving equality here. Sorry. Now, how do I construct this subset Q with a given independent set X? And that is almost the same as we did it for constructing minimum cuts with a given maximum flow. Okay, so remember how we did it in the maximum flow problem. We were just defining this minimum cut by looking at all the vertices which were still reachable from the source in the corresponding residual graph. And we do something which is almost the same here, namely we define this set Q, subset of the elements, as all the elements on both sides which are reachable from this subset of vertices Sx. Okay, so when you look into this figure here, we define Q to be everything that is reachable on directed paths from vertices or from elements in the set Sx. Okay, and that was what defined me some subset of the items, both containing elements in X and also containing elements not in X. Okay, so we have Q here, the upper side, we have the complement of Q here on the bottom. The first important observation that we can make is this one here, namely the so constructed set of elements Q does not contain any element from Tx. And that is because we started with a set X, an independent set X, such that no directed path exists anymore from any elements in Sx towards the elements in Tx. So therefore, these elements Tx down here are not reachable from here, and therefore the whole set Tx is in the complement of Q. Now what did we do? Given some independent set X, with the property of non-existence of augmenting paths, we constructed some set of Q of the elements. And in order to get equality here, we are going to show the following. The first claim says that the number of elements in the intersection of X and Q is equal to the rank of subset Q, in this case with respect to matroid number 2. Okay, and we're going to show that the number of elements in X without Q is equal to the rank of E minus Q. Okay, in this case with respect to matroid number 1. So that means we will, if we have equality here and here, we will have that this is equal to the rank of Q and this is equal to the rank of E minus Q, and hence we get equality here, and that's exactly what we need. So let's look at the first claim here. Of course, this is always smaller or equal, right? Because this is an independent subset of Q, and this is the size of a maximum independent subset of Q. So smaller or equal is always true. So let's assume for contradiction it would be strictly smaller. So size of X together with the intersection of X and Q is strictly smaller than the rank of Q with respect to this second matroid. Well, then I could still augment this set, this independent set, and therefore I know that there exists an element F which is contained in Q but not yet in X, so that I can still augment it and remain independent, so that X intersect Q together with this new element F is still independent. Okay, and that is in this picture this element F up here. So it's contained in Q but not in X. And I claim that if I add this element F to X itself, this is not going to be independent. So this is not independent with respect to matroid number 2. Why is that? Well, that's because all the elements F that can be added to set X, they are contained in the set Tx, right? But this element F is actually part of Q. Okay, so let me write that down. F is chosen from Q, and Q has no intersection with Tx by construction of Q. So if you look in the figure, F is indeed chosen as being an element of Q, so on the upper part, and the set Tx is in the complement of Q. So this element F could actually also be part of Sx, that wouldn't matter, but the most important thing is it lies in Q and hence has an empty intersection with Tx. Now, since this is a dependent set, it contains a circuit. So the circuit with respect to matroid number 2 that I get when I take X and add the element F, and I claim that this circuit contains an element from X that is not in Q. So this contains an element E, where E is from X but not in Q. Why is that? Well, this is a dependent set containing element F, okay? And when I look at the elements from X, which are also contained in Q, I can still add this element F and still remain independent. So if I want to extend this into a dependent set, I must choose at least one element which is not already contained in Q, and that is exactly this element E here. Okay. In the picture, that would be this element E here, and now you see that this element is sitting in X on the left-hand side, but not in Q. Okay, so it's on the bottom. And now we have found something that shouldn't be there, because we have found this element E, which is in the circuit generated by adding element F to X. Okay, so this element E is in the circuit that I get when I add this element F to X. And hence, when I remove this element E from that circuit, I again get a independent set. But that means that this edge should be there in the graph, because our graph has all these directed edges from elements F to elements E when this element E appears in the corresponding circuit for F. So in writing, that would mean that this edge F, E would be part of our graph for matroid number 2, and that's a contradiction to the construction of the set Q, because now we have found an element E which is reachable from element F, and element F was an element that was reachable from Sx. So we have found an element E down here in the complement of Q, which is reachable from the set Sx, and that's a contradiction to our own construction. Now the rest of the proof goes along the same lines, so we would assume that we have not equality here, so that would be a strictly smaller, so we would have that X without Q is strictly smaller than the rank, now with respect to matroid number 1, of the set E minus Q. And that again means that I can extend this independent set by one additional element. So that gives me the existence again of an element F, which is now contained in E without Q, but also not in X. Again, so that X without Q, including this edge, F is still independent with respect to the first matroid. So in the figure, that is this element here, and then actually the same sequence of arguments will give me another element E here, which is on the left-hand side in X and also in Q. So that's going to be an edge E in X intersect Q, so that this edge E is also contained in the circuit that I get when I add F to X. And that is this element E here. Oops. So this element E here. And that means again that we would have to have the corresponding edge E, F in our augmentation digraph A1 with respect to X. And that's again a contradiction, because this element here is reachable from Sx. And now I have this edge, I have found this edge here, so that means this element, which is outside Q, would also be reachable, and that's again the same contradiction to the construction of the graph. And that finishes the proof of this augmenting path characterization. So once again, what did we show? We showed that for each independent set X in both matroids, we can do one of two things. Either we can find an augmenting path in this augmentation digraph, and that means we could increase the size of this jointly independent set X, or we do not find such an augmenting path anymore in this augmentation digraph. And in that case, we can always construct a set Q of elements that achieves equality in this weak duality inequality. So that means we can then give an optimality proof. So not only do we have inequality here for all independent sets in both matroids and all subsets Q, but we can also construct an independent set X in both matroids and a set Q that achieves equality here. And that means we have proved this min-max relation again, this duality result, which is due to Jack Edmonds from 1970. So which just summarizes what I just said. The maximum size independent set in two matroids is equal to the minimum of this sum of these two rank functions taken over all subsets of the elements Q. Yeah, weak duality is what we showed earlier, and I just showed you how to construct independent sets and sets Q such that we can achieve equality here. And that actually means that we have our completeness proof, correctness proof of a very simple and generic matroid intersection algorithm, which is this. We start with an arbitrary independent set in both matroids, could be, for example, the empty set. And as long as we find augmenting paths, so Sx, Tx augmenting paths in this augmentation digraph dx, we apply the augmentation lemma and increase the size of the set X by 1. And when we exit this while loop, there is no such augmenting path anymore. And by the previous theorem, we will have computed a maximum independent set in both matroids. Now the correctness of this algorithm follows directly from all our previous observations and this augmenting path characterization that we had earlier. And the final word is again on computation time, and I try to be brief. So in order to say something about the computation time, we have to say something about how much time it takes in order to verify if a given subset of items is independent in one or the other matroid or not. Okay, so let us assume that such an independence test for any of the matroids takes that computation time, order g of n for some function g, say a polynomial function in the number of elements n. And then the theorem says that this generic algorithm on the previous slide solves the matroid intersection problem in computation time n to the 3 times g of n, where g of n is this independence test in any of these two matroids. So how do I come up with this n to the 3 here? I try to explain that on the next slide. So of course we have at most n augmentations because each time we increase the size of the set X by 1. So that can happen at most n times, with n as the number of elements. And each time that we do that, we have to build the corresponding augmentation digraph. And that means for all the elements F that are not yet contained in X, and well, if in case that I cannot add them with respect to one of the two matroids, I have to figure out which edges I have to introduce. So that means for all the elements which are already in X, I have to check if this element E would destroy the corresponding circuit that I get when I add the new element F. Okay, so this is an independence test that I have to do, and I have to do that for both matroids actually. And that means if I look at how often do I have to do these independence checks here, that means this is for all elements that I do not yet have. That's at most order n many. And this is twice for all elements that I do have in set X. So that's again order n many times 2. And or twice I have to do an independence check. And that gives me an order n squared times g of n where g of n was the time for the independence test. So altogether, that gives me n times order n squared times g of n. And once I have built this augmentation digraph, I of course also have to find the shortest augmenting paths in this bipartite graph. And without going into too many details, but that can be done by one run of the breadth first search algorithm from all these SX nodes simultaneously. And that is possible in time linear in the size of the graph, where order n squared is an upper bound on the number of directed edges in this augmentation digraph. So then I would have again n times order n squared, which is n to the 3 again, and the computation time is okay. So that is summarized here once again, and that finishes the analysis of the matroid intersection algorithm by Edmonds. Important thing to realize, maybe in the computation time, I didn't say it explicitly, but this is shortest paths with respect to edge lengths equal to 1, and therefore we can use BFS and we don't have to use something like Dijkstra. So coming back to the main theorem of this lecture, we can solve the matroid intersection problem in time which is polynomial in the size of the ground set, and of course it has to be polynomial in the time it takes to verify if a given subset is independent or not. Now, nice, so we can do it for 2 matroids, but the question is, can we do maybe the same for 3 or more matroids? And it turns out that this is not the case. So a little bit later, there's going to be an exercise once we have introduced the concept of NP completeness to show the following. If there are 3 matroids, M1, M2, M3 on the same ground set, and you give me a number k, then it is NP complete, so it's computationally hard in order to decide whether there exists a set F which is independent in all 3 matroids, which is large enough. Okay, so that's an exercise that we are going to solve. And that means that it is very unlikely that we have an efficient algorithm that can compute maximum independent sets simultaneously in 3 matroids. So we will definitely come back to that later, but that's an interesting observation because it says that the complication of the combinatorial structure for the intersection of 2 matroids, that can always be solved in polynomial time as long as this independence check can be done in polynomial time. But as soon as I add even more complication and I intersect 3 matroids with each other, in general, that can be a hard problem. So it doesn't have to be, but it can be a hard problem. Okay, so something like that cannot happen if I only intersect 2 matroids with each other. So that is interesting, and maybe one of the final messages of this lecture. And with this, I will essentially end the part on matroids or matroid intersection. And the next lecture is going to be again on flows, and in this case, minimum cost flows in directed graphs. Thank you for your attention.